Don't want to, okay. All right. Okay, so I got about 30 more slides. Should take about 20 minutes or so, and then I'll let you guys go early, okay? So the first method was to do what's known, the previous method I talked about was known as the phase shifting method. So you generate a composition of signals where you have, the first part is your DSB-SC signal, and then the second part is a Hilbert transform version multiplied by sine. And then depending on whether or not you subtract or add, you would generate your upper or lower sideband, okay? So there's another method which is pretty obvious, and you probably would think about it and go, yeah, this kind of makes sense, is why don't you use a bandpass filter where you just filter out exactly the sideband that you need, right? Specify a bandpass filter where the bandwidth is exactly equal to the bandwidth of your signal, and just center it whichever sideband you want. And then you just filter that out and choose, and that's the sideband that you get. Kind of makes sense, right? That's what's known as the selective filtering method. Okay? So that's what the selective filtering method is called, and this is actually the most commonly used technique to generate single sideband signals, because unfortunately a Hilbert transformer is a non-ideal device, so it's actually quite difficult and not impossible to create an actual generator that'll actually phase shift every single frequency component by pi over 2. Okay? So what people do instead is they do what's known as the selective filtering method, where you just have a bandpass filter centered at whichever component you want to, or whichever sideband you want to get out, and that's what you choose. Okay? So this requires the two following assumptions. The first is that you have to make sure that the bandwidth of the message signal is much, much less than the carrier frequency, which actually makes sense. Okay? Now, the next situation is a little unorthodox, but it will make sense once I show you some diagrams. The message should have what's known as a frequency hole around f is equal to 0. So what this means is that if you have a baseband signal with your spectrum, this means that from 0 up to some frequency, they should have no frequency values. So what I mean specifically is that your message signal would look something like this. Okay, this would be your spectrum of the message signal. So this here is what is known as a frequency hole. So from 0 up to some frequency, which we'll call f of 1, there should be no frequency content, but the rest of it should be. Okay, and I'll talk about why this is important very soon. But this is one of the criteria they have to impose when you want to generate single sideband signals using selective filtering. Okay, so it's basically a two-step process, as you can figure out. First, generate a double sideband suppressed carrier signal, so you have your upper and lower sidebands that are generated, and then have a bandpass filter that'll select out which sideband you want. If it's upper or lower, it doesn't matter. Okay. Okay, so why should we have a frequency hole? Okay, and this diagram should pretty much explain to you why. Okay, so this is what the spectrum would be of the message signal, without any modulation, and this is what it would look like when you're doing double sideband. So remember, this is positive this is the positive side only. Okay, we're not going to do the negative side, because you can assume that's symmetric. So this is positive side only. Okay, so without a frequency hole, you would need an ideal bandpass filter. So what it means by ideal is that, you remember what an ideal low-pass filter is. So you have basically, it's a flat line, and then right at your cutoff, you have a straight line down, right? But you know from electronics that it's very impossible to create an ideal low-pass filter, or a bandpass filter. That's what it means by ideal, right? Because in theory, it would be nice, but in practice, it unfortunately won't fly, okay? So without a frequency hole, what this means is that you would need an ideal bandpass filter to be able to successfully create that single sideband. That's why you need a frequency hole, because when you have a practical bandpass filter, you've got that little bit of tolerance from where your cutoff is to where it's what's known as the transition band, right? So you want to have a frequency hole that is the same width as the transition band, so that anything in between the transition band you don't care about, but then after that transition band passes, that would be the actual frequency content you get. That's why you need a frequency hole, because without it being ideal, you have to have that transition band to realize a practical bandpass filter. Okay? So this diagram is actually a better representation of what I want to talk about. So if there's a frequency hole, remember that from 0 up to some frequency f1, there are no frequencies, right? So this is all no. Okay? So this is what it would look like. So this is the ideal case. Okay, and this is, I guess you'd call this the real case. So in the real case, if I were to modulate the signal, you'll see that everything is transferred over. This is f of c here, as we talked about, and then when you actually generate an ideal bandpass filter, this here is what's known as the transition band, and this would be a realizable bandpass filter. So this is a realizable bandpass filter. So you can certainly design the right electronics to actually do this. And if you have a bandpass filter with a transition band, it's good, because anything in between the transition band you don't care about. It's the single sideband we need at the end. So what we're concentrating specifically is this range, right? We don't care about the transition band, so that's actually what you get. That's why you need to have a frequency hole. It's because from 0 up to some frequency, whatever that is, you want to make sure that that width spans the transition band, so when you actually create a realizable bandpass filter, you'll actually be able to successfully get whatever sideband you want. Okay, so that's the reason why you want a frequency hole. So if you want to demodulate a single sideband, so we're going to talk about demodulation now. It's actually very simple. All you have to do is use the same methodology that you would with double sideband suppressed carrier signals. You just multiply by a coherent detector. In this case, you will multiply by a cosine, right? And you have to make sure that the carriers are synchronized so that you're able to demodulate correctly. And okay, we can certainly do that, all right? So your single sideband signal, remember, it's either MFT cos, and it's either minus or plus. So the minus would be the upper sideband, and the plus would be the lower sideband, right? So this is what the signal that is coming in, and then when you multiply by cosine wave, you go ahead and you expand this out, right, like this and like this. So the multiplication of the two coses becomes cosine squared, right? And then you have sine times cos. And remember the property where sine of 2x is 2 sine x and then cos x, yeah? And then when you multiply by a half, you just get rid of this, and that's where this guy comes from over here, okay? And then this is standard, so cosine squared is simply a half plus a half cos 2x, and that's where this comes from, okay? So when you multiply by a cosine wave with a single sideband, you'll have a bunch, you have 3 terms, and then that's when you apply a low-pass filter, because you want to get rid of the 2 omega c components. So when you apply the low-pass filter, the last 2 components go away, and then you're left with this one, which is your original message, which is what you wanted anyway, all right? So you want to make sure that the low-pass filter, the passband or the range is up to the bandwidth of your signal, which makes sense. And once you do that, then these 2 components simply go away, because these, when you actually, when you remember, this is modulation, so you have plus minus 2 omega c for either one, and then when you apply the low-pass filter, those 2 go away, and then you're just left with that. Okay, and that's what you get. So the reason this is approximate because there's a scale factor. So if you want to get rid of this half, just have some sort of gain stage that'll multiply every single point by 2 to get rid of the half. Okay, all right. So let's get on to the next part, which is vestigial sideband. I'll talk about that soon, what it actually means. But let's talk about what we've discussed so far. So if we have 2 signals with a bandwidth, the bandwidth is going to be b hertz, okay? If we have 2 signals, we can use quadrature amplitude modulation. So you have 2 signals that are independent, you transmit them through your channel, and then you have 2 signals that are independent together that occupy the same space, okay? So you have 2 signals that are occupied twice the bandwidth, okay? If MFT has a frequency hole that around f is equal to 0, then you can use single sideband modulation. So this is using the selective filtering method, right? So we're talking about all of the methods that we've seen so far in generating, amplitude modulated signals. So this is selective filtering, okay? If your message, however, has significant low frequency energy, so what that means is that if your spectrum looks like this, right? If there's no frequency hole, so no frequency hole, what exactly do you do? Right, so you can use the phase, you can use the phase shifter if you want, but that's not practical. So phase shifter is, non-realistic. It's non-realistic, unrealistic. This is actually not good. It's possible to do it with a sine wave, but in terms of like anything else, it's a little difficult to do. Unrealizable. Okay, so how exactly would you generate a single sideband modulating signal if you had a situation like this? Significant low frequency energy looked like this, right? So that means that between 0 and f1, there is still quite a bit of, components. So what exactly would you do in this case? Well, let's talk about varying degrees of bandwidth. So if you wanted to transmit one sideband, the B of t is what's known as the transmission bandwidth. It would just simply be the bandwidth of your message. That's totally fine, okay? Then you have the opposite side of the spectrum, which is double sideband, where if you want to transmit the signal, you have to transmit both sidebands, and the bandwidth requirement is twice the bandwidth. So this is where we're going to go from low to high in terms of what's required for transmission. So the lower end is the better case, where you have just one sideband, and the higher case, the very high end, is transmitting both. Okay? So what we can do is if you want to be able to transmit single sideband, you can certainly come to what's known, you can certainly come to a compromise. Okay? The compromise is what is known as vestigial sideband modulation. So vestigial sideband modulation. Okay? So what the vestigial sideband does is that it comes to what is known as a compromise. So what it means is that you can transmit one sideband almost complete, so that means there's a little bit of imperfections, and the other sideband you're just going to transmit a little dinky bit of it, or just a trace or what's known as a vestige of it instead. So this comes from a compromise, and this is actually a little more realizable. So if you want to save in terms of bandwidth, single sideband is a little difficult to do. Double sideband is basically too much. So if you want to come to a compromise in bandwidth, you can use what is known as vestigial sideband modulation, where you transmit almost maybe 85 to 90% of one sideband, and then you transmit maybe 10% of the other together to make 100% of modulation, 100% of bandwidth. Okay, so here's a quick diagram. All right, so here is the original spectrum, right, which we'll call M of F, and then this is what happens when you perform double sideband suppressed carrier. So again, we're just going to take a look at the positive side only. Okay, we're going to take a look at the positive side only. So when you do a vestigial sideband modulation, this is what the output would be. So remember, this is split down the middle, so this would be F of C. So what's happening here, if we split it down the middle, is this is the almost complete part, so this is almost complete. And we're going to take a look at the upper sideband here for now. Okay, and then this is a trace of lower sideband. Okay, so a little bit of the upper sideband is missing, and only a small part of the lower sideband is retained. And then if you transmit this over your channel, this is what is known as vestigial sideband modulation. Okay, so you got most of the upper sideband or most of the lower sideband, and a little bit of the other one that you're missing. And then you transmit that together, and that would be the actual transmitted signal. And if you had this as being transmitted, then the demodulation techniques are actually a little more better to realize. Okay, and that's the reason why we want to take a look at vestigial. So it's a compromise between the two. Okay, so let's just review the selective filtering method for single sideband, right? So it's a two-step process, right? So remember, you generate a double sideband suppressed carrier signal, and then you want to filter out one of the sidebands to get your actual single sideband using a bandpass filter. And it's actually the same approach using vestigial. It's just that your bandpass filter is going to be a little different. So instead of it being ideal for the single sideband, you want to make it non-ideal. And then if you do that, then you can certainly go ahead and do vestigial. All right? So it's actually basically the same process. It's just the bandpass filter is what's going to be a little different. Okay, next. Come on, next. Okay. So this is one particular example of what a vestigial sideband will look like. So remember, this here, you can think of that as the transition phase from before. Right? So this is the transition phase. But now what's going to, the transition band. But now what's going to happen is that we're assuming that there are no frequency holes centered around 0. Okay? So if I decided to modulate, so remember, this is the same process as doing single sideband. So first modulate by your carrier frequency, which is F of C. So this is the positive side only. Okay? And then if I applied a correct bandpass filter, so this is one example of what a vestigial sideband will look like. So anything after the carrier frequency here, right? So remember, this is the carrier frequency, and this here, F of V, you can think of that as your F of 1 from before, okay? So if you were to actually filter this out, notice that the carrier frequency is right here. So this is in between the transition bands. So in between, the carrier frequency, and you can consider this as, F of 1, right? Remember, you're transmitting it over, but so part of this spectrum is incomplete. It's actually, decayed and gained a little bit. But the rest of the actual spectrum is going to be the same, right? So between here and here, it's pretty much going to be the same. Okay? So what's happening here is what is happening is between here. So the transition band makes this important if you want to do vestigial sideband modulation. So part of the upper sideband gets a little screwed up a little bit, and then you really want just a trace of the lower sideband, and that's what you want to transmit in the end. Okay? So what conditions do we need on this bandpass filter in order to get vestigial sideband generation? So how exactly do we design this? So what is the design process? What exactly do we need to do? How do we design this bandpass filter so we actually do get a vestigial sideband modulated signal? So let's actually, we'll wait and we'll figure out how to do that. Let's actually figure out how to demodulate the signal first. And then once you see that, then we'll actually be able to figure out what exactly those conditions need to be. Okay, so if you want to demodulate a vestigial sideband signal, it's actually the same as using double sideband suppressed carrier when in terms of demodulation. You use a coherent detector. So that means that you have a cosine wave on the receiving end that'll perform the demodulation for you. And if you take a look here, we multiply by a 2 for convenience, because if you remember, when you're doing modulation for double sideband suppressed carrier, there's a factor of a half. So if I multiply by a 2, it'll get rid of that constant of a half and you get the original signal back. Okay? So this is just for convenience. Okay? So you have a vestigial sideband signal coming in, you multiply by your cosine, you apply a low pass filter, and then you get the original signal as, you know. So it's basically the same process as doing coherent detection for double sideband. So S of t is what is received, so this is when you multiply the cosine wave, so that's what we get, right? So it's vestigial times your 2 cos. And then if you perform the Fourier transform, right? Remember the 2 cancels out the half, so this is actually what you get. So we're going to take the carrier frequency, which is located at f of c, and then you're going to do plus minus f of c with the spectrum, right? Because you're taking the Fourier transform, that's what you get. So this is a diagrammatic representation of what is going to happen. So remember, so this is, so let's see here. So remember your, let's see. Yeah, so what's going on here? So, right, so this is what your vestigial sideband modulation looks like, right? So remember this is split down the middle, right? So this is, you know, this is your upper sideband, almost, right? And this is lower sideband, a little. Right? And then you also have it on the other side. So if I were to take this and if I were to first shift it to the right, this is what happens here, right? So this component is here, right? And then if I take this and shift it to the left, this is what I get over here. And then when I add them up together, notice that because these 2 signals are symmetric, if I actually add them up together, when these cross over, you will get the original spectrum back, which is actually quite nice. Okay, so you can actually, so this is actually a diagrammatic representation of how you can actually demodulate. So this is, you know, this is how you show it diagrammatically. And then you can obviously filter these out using a low pass filter, right? To get rid of those. And then you get the original signal back. Okay, so now that we know how exactly that's supposed to work, okay, how exactly do we design this guy in order to be able to perform successful demodulation? So how exactly do we do this? So how do we figure that out? Well, we do know for a fact that, you know, when we demodulate, it's still the same thing as using a coherent detector, which is great. That's cool. But then how do we actually figure out this? This is what we need to figure out now. Okay. So let's go ahead and let me just start from the beginning. Let's go from the beginning here. So this is the original message signal. The first step is to perform double sideband suppressed carrier modulation. So you multiply by your cosine, which is fine. Okay, so when you actually do the Fourier transform, this is what you get. Okay, and the constant k there is to account for the half, but in general it may be something different depending on whatever the amplitude is for all the amplitude values for m. So we just apply a k here, just because what's going to happen is that when you do the modulation, this may be a half. Okay, but in general it may not. So just put the k there just to make it the general case. Okay, so once we perform this modulation, we're going to pass it through your bandpass filter, right? And then once you pass it through your bandpass filter, this is your channel, which we'll assume is ideal for now. So right now, what's happening is that we're taking our modulated signal and multiplying by your bandpass filter, right? Because this is convolution, which is multiplication in frequency domain. Okay. So now that we're here, we're going to take our signal, multiply by, you know, your 2 cosine, and then this is what you get. This is what the modulated signal is from before. And then finally, the output is just your low-pass filtered version of whatever's coming in, you know, on the demodulation side, which is nice. So this is the, you know, the impulse response or the, you know, the in and out relationship for the low-pass filter. Okay. So let's take a look at this very slowly. So we need to take a look at what the output spectrum looks like. So this here is simply the demodulated signal. So you take your VSB modulated signal, you multiply by cosine, and then you apply a low-pass filter to it. Okay, so that's what's happening currently. Okay, so if you remember from before, S of f, right, is equal to because we're multiplying by a 2 cosine omega ct, right? So that's what's happening here. This is being modulated. Okay, so let's see here. VS, BSC, and then M of F. I'm just double checking why this is VS. K. I'm trying to figure out why this is happening here. Oh, I see what's happening here. Okay, so let me see here. Let me just double check what okay, here. Right, this is it here. So this is this relationship. So what's happening here is that if this is what the equation is for the VSB, remember, if I decide to shift this by f of c, then what's going to happen is that you're going to take this expression and do a delay by f of c. This becomes k m f of 2fc, right? And then plus m of f, because minus fc plus fc, becomes 0, okay? And then multiplied by hv f of fc. So that's what's happening here. We're taking this equation and we're shifting it to the right by fc. And that's what's happening over here. Okay? That's what's happening here. This is the first part. So this here is this guy. Actually, let me just do that. So this here is this guy over here. Okay? Now this is the same process, but you're just delaying by negative now. So that's what we get over here. Okay? So that's what's happening here. All right. So now when we apply a low-pass filter, remember, anything that is undefined, remember, when you're going beyond the bandwidth of the message signal, we filter those out, okay? So when you apply your low-pass filter, these components at 2fc will go away eventually. But so what we're going to do now is we're just going to do some factoring. So if you take a look, there's some components of m of f, which we've gathered over here, and some components of m of f2 minus fc and 2 plus, which you've also gathered over here. So we just did some rearranging here. Okay, so when you do that rearranging, so this component here is this guy over here, which makes sense. Because remember, what you're doing is, remember, you're shifting the spectrum to the left and to the right. So this is actually defined over here. And then these guys are over here. That's what's defined by the plus and the 2 and the minus. So that's what's going on over there. Okay, so that's this guy and that's this guy. That's fine. And then when you apply a low-pass filter, these components get filtered out. And then this is what is remaining. All right? So, if you want to design a vestigial sideband filter, okay, you have to make sure that when you get the original signal back, you want to basically get this guy. But then there's some stuff here that is being multiplied to amplify it a little bit. So, in order for you to successfully demodulate the signal, you have to make sure that this entire value here is constant. And that's what's going on here. So that's why this is here. So if you want to design a vestigial sideband bandpass filter in order for you to generate the correct signal in the output, you have to make sure that when you take your bandpass filter and if you shift to the right by fc and shift to the left, when you add everything up, the output becomes a constant in between the two values, in between the in between the bandwidth, the plus and minus. So that's how you design your bandpass filter to get a vestigial. Okay. So there's another situation as well. So this is the result that we have here. Okay, the above condition also implies the following. So this means that if you were to, I won't show you the math for this, but this implies this situation here. So this means that if you have some frequency f of v, right? So it's centered at f of c here. This means that in between plus and minus, it has to be symmetric. I won't actually prove that, just take my word for it. But this will imply this situation. So if you have some carrier frequency plus minus some desired frequency, some vestigial frequency, it has to be symmetric. Okay? Okay, so let me just blow through all this. This is my last slide for you. Okay, so come on. Okay, so vestigial sideband modulation is a compromise between double sideband and single sideband modulation. Okay, so if you wanted to determine the single sideband modulation, if you let this frequency value, this f of v value here, if you let this approach 0, if you made this 0, what's going to happen is that you will only get this guy over here, which is single sideband. Okay, if you made the value approach the bandwidth, then you're actually making a double sideband. So the transmission bandwidth is the following here. So you have single sideband, which is the best transmission you can come up with, and then you have vestigial sideband, which is somewhere in the middle, and then you have the double sideband, which requires twice the bandwidth. So in practice, vestigial sideband modulation requires approximately a 25% increase in transmission bandwidth. So this means that whatever bandwidth you have for your message, you multiply that by a 25% increase, and that's how much bandwidth you would approximately get if you did vestigial sideband. Okay? So if you did vestigial sideband modulation with a carrier, right, so single sideband with a carrier, so what you can do is if you decided to add a carrier, so instead of, so this is a carrier, so this is for, let's see, envelope detector, I guess. So you don't have to do it, using coherent techniques. You can certainly use an envelope detector if you wish. But if you decide to add a carrier on top, you're still going to get very bad efficiency. So if you decided to add a carrier with your single sideband, it's actually even worse than just considering amplitude modulation, the efficiency, which is the maximum of it being a third. So it's actually still quite inefficient, even though if you try to add a carrier and if you decide to do an envelope detector, it's still efficient. So that's why you want to use coherent demodulation to detect these signals. Okay, so that's it for me. Sorry I went a little overtime here, but I'll let you guys go now. So in terms of what you're responsible for the midterm, up to this point is what you're responsible for. Okay, so anything starting from the beginning of when we met, which is about mid-May, up to this point, is what you're responsible for the midterm. Okay, so any material that you'll see from this point onwards will not be covered for the midterm, but it will be for the final exam. Okay, so I will also do an additional tutorial for questions on amplitude modulation the next time we meet, the next class. Okay, and if you take a look at those questions and then any of the other questions that are in the past midterms and all, if you can do those successfully, then you should be in good shape for the midterm. Okay, so that'll be it for today. When I see you next Wednesday, we'll talk about a little bit more about coherent demodulation, especially what's known as the phase lock loop. Okay, so I'll see you next week.